Come on, my dears, let us proceed further in chapter number 7. See, if you remembered, in the beginning of this chapter, we had talked about N-type semiconductor and P-type semiconductor. If you take all alone only N-type semiconductor or only P-type semiconductor, it has got no applications in practice. It is of no use. Then what we had done, we had joined them. One N-type semiconductor and one P-type semiconductor, when they are joined, it gives us, come on, PN junction diode, correct? And then that PN junction diode could be utilized for various purposes. We could have rectifier, remembered? Fine. Then we had prepared Zener diode, which can just do the job of voltage regulation, correct? Then we had prepared solar cell, in which electrical energy is converted into light energy. Then we had prepared photodiode, in which light energy is converted into electrical energy, correct? So all these different types of semiconductor devices we could get only after joining P and N type semiconductor, correct? Now let us do one thing. Let us join one more P type semiconductor or one more N type semiconductor with a PN junction diode. Then we will have one component which will have two PN junctions, and such a component is known as transistor. What is it called? Transistor. How does it have two PN junctions? I am showing you. But this transistor is very, very important in the study of electronics. This component is essential, transistor. And that transistor was discovered, it was prepared first by three scientists working at Bell Telephone Laboratory at USA in the year 1948. You will require to remember their names because these names are given in the textbook. What are their names? Look, Mr. John Bardeen, then Mr. Walter Brattain and Mr. William Shockley. Look here, Mr. John Bardeen, Mr. Walter Brattain and Mr. William Shockley. These three scientists had prepared very first transistor, and they were rewarded with a Nobel Prize for the preparation of such a important electrical component. Okay, fine. Now, this transistor word is prepared by coining two words. Certain letters are picked up and then they are joined. Then the word is prepared is transistor. And which are those letters? I am showing you. Transfer of resistor. From this phrase, we just pick up this word trans, and here, come on, istor. Pick up trans from here, pick up istor from here, join them, trans plus istor, that makes transistor. Okay, fine. Now let us see what is that transistor. Transistor is of two types. One is NPN transistor, another is called PNP transistor. Here it is, NPN transistor, another is PNP transistor. Fine. Now tell me how it is prepared here. Here one P-type semiconductor is sandwiched between two N-type semiconductors, and here one N-type semiconductor is sandwiched between two P-type semiconductors. Okay, both of them have two PN junction. How? I am showing you. Hide this N-type semiconductor, then you will have one PN junction here, and if you hide this one, then this is another PN junction. So a device having two PN junctions is called a transistor. So this becomes now transistor. Similarly here also, if you hide this, you will have one PN junction. If you hide this, you will have another PN junction, correct? A device having two PN junctions is called a transistor. Fine. Now, here in this transistor, actually the volume is very small, correct? It is perhaps the size of smallest ground nut. Smallest ground nut if you have, then its size is very, very small, as much as, come on, as I said, smallest ground nut. Okay. Now in that very small size, there are three parts of unequal volume. Three parts of unequal volume. And the middle part, which is of smallest size, is known as base. B for base. B for base. Correct? Then this part having largest volume among these three parts, it is called collector. C for collector. C for collector. Okay? And this part having medium volume, moderate, in between, it is called emitter. E for emitter. E for emitter. Correct? Emitter, base, collector. Emitter, base, collector. Similarly, here also, the part having smallest volume is called base. The part having largest volume is called collector. And the part having intermediate volume is called emitter. Fine. Emitter, base, collector. Fine. Now these are the schematic diagrams which gives you idea about the construction. Now let us see what are the internationally accepted symbols, circuit symbols for these two types of transistor. Come on. For NPN transistor, this is the circuit symbol. For PNP transistor, this is the circuit symbol. How I am showing you? See, emitter, base, collector. Emitter, base, collector. If it is NPN transistor, then you can write NPN this way or NPN this way, no problem. And if it is PNP transistor, you may write PNP this way or you may write PNP this way, no problem. Now we just differentiate between these two symbols by putting one arrow only on emitter. In case of NPN transistor, that arrow is shown, come on, outward. That arrow is shown outward. And in case of PNP transistor, that arrow is shown inward. This arrow is shown outward and this arrow is shown inward. Actually, it is to be shown in the direction of flow of electric current in the emitter base junction. Here in this emitter base junction, the direction of flow of electric current is from positive to negative. That is why it is outward this way. And here direction of flow of electric current in emitter base junction is from positive to negative this way, inside. Okay. Here outward and here inward. Okay. Don't make any change in these symbols because these symbols are accepted internationally. Okay. Fine. Now these three parts of transistor, emitter, base and collector, they differ from other aspects also. First aspect, let us compare their volume. Come on, as I said, base has smallest volume, this collector has biggest volume and emitter has moderate volume. What about amount of impurity? Amount of impurity added in emitter is found to be maximum, correct? Amount of impurity added in base is minimum, and here for collector it is moderate. What about resistivity? Resistivity of emitter is minimum. Resistivity of base is more, and resistivity of collector is moderate, medium. Okay, fine. So just remember this comparison table for these three parts of a transistor. Okay. Now there are two junctions, two PN junctions in a transistor. One is between emitter and base. We call it emitter base junction. It is this. And another is collector base junction, which is this. Correct? Now, whether you say emitter base junction or only emitter junction will do no problem. Whether you say collector base junction or only collector junction will do no problem. Look, emitter base junction or shortly emitter junction. Collector base junction or shortly collector junction. Correct? Remember, there are two types of transistor, NPN and PNP. But each of them has three terminals, emitter, base, collector. Now out of three terminals, if you desire, any one terminal can be kept common in the input part of the circuit and in the output part of the circuit. Depending upon which terminal you are keeping common in the input and output part of the circuit, we will have three different modes of connection with a transistor. They are respectively known as common base, common emitter, common collector. Common base, common emitter, common collector. Out of these three types of connections, look here, common base, common emitter, common collector. CB means common base, CE means common emitter, CC means common collector. Out of these three types of connection, in our syllabus we don't have to study about common collector, no. Now we will study these two types of connection, common base and common emitter. In textbook they have not described in detail about common emitter, we will study that also, okay. They have described this common base with a proper figure. Let us see both the types of connection, common base also and common emitter also, one by one. First of all we take common base connection. Remember, whatever the type of transistor may be, might be NPN, might be PNP. Whatever type of mode of connection may be, might be common base mode, might be common emitter mode, might be common collector mode. Irrespective of that, remember every time emitter junction is always given forward bias and collector junction is always given reverse bias. Emitter junction always forward bias, collector junction always reverse bias. Let us see now. Common base connection of NPN transistor. Just to show the same transistor, NPN, I have shown here, correct? Horizontally I have placed NPN. You may write NPN from here also, no problem, correct? Now the central part having smallest volume is called base, correct? And this part having largest volume is called collector. This part having intermediate volume is called emitter. Fine. Right now emitter is N-type semiconductor and collector also is N-type semiconductor. So I am showing you majority charge carriers in N-type semiconductor as free electrons and minority charge carriers as holes. Here also majority free electrons and minority are holes, correct? What about this part? This middle part is called base, and base is made up of P-type semiconductor in this case. In P-type semiconductor we have majority charge carriers in the form of holes, fine, and minority charge carriers are in the form of free electrons. Got it? Now tell me, emitter is to be given always forward bias and collector is to be given reverse bias. When you are making this emitter forward biased, this depletion layer would be rather thin, narrow, and when you are giving collector junction as reverse bias, then naturally here the depletion layer would be wide, okay. Here width of depletion layer is less because of forward bias, here width of depletion layer is more because of reverse bias, fine. Now let us start working of this device, working of this circuit. As I said, if emitter is to be given forward bias, then N with negative, you can see N with negative, okay, fine. And if collector junction is to be given reverse bias, then N with positive. This reverse voltage is more than this forward voltage, so here I am showing two batteries, okay, here one battery and here two batteries. EMF of this battery connected with emitter, I just show it by symbol VEE as per the textbook. EMF of this battery which is connected with collector, I am showing by symbol VCC, correct? Let us start now working. This negative terminal is connected here, so this terminal is negative, fine. It will simply repel these free electrons which are majority charge carriers in emitter, and because of repulsion provided, come on, electrons will start flowing this way, come on. They will enter from emitter into the base. And out of that number which enters from emitter into base, hardly maximum 5% of electrons happen to combine with the holes. How many number? Only maximum 5% of the electrons associate with the holes. Then you may have a question, why only 5%? There are two reasons. The region of base is extremely thin. Actually it is introduced in the form of a very thin chip, CHIP, chip. Very thin strip, okay, fine. And so because its width is very small, electrons do not take much time to cross that width, and that's why there are less chances for recombination of electron with a hole, correct? And one thing more, in base, come on, amount of impurity is minimum. Because amount of impurity is minimum, number of holes itself is minimum, so reducing the chances for combination of electron and hole. In practice, we find hardly 5% of electrons entering from emitter into base associate with the holes. And after associating with the holes, those electrons simply jump downwards this way, because this terminal is at higher potential. This terminal is at higher potential with respect to this. Electrons will be just transferring from one to another hole, second to third hole in the form of bound electrons, and they will be coming this way. I mean, they will be flowing in the outer part of the circuit this way. Fine. What about remaining 95% of electrons? Remaining 95% of electrons are delivered into this collector. The same thing I have shown here using one arrow. Starting current is 100%, 5% is diverted through base, and remaining 95% is delivered into this collector. Got it? Fine. If you can draw this arrow is well and good. If you cannot draw, no problem. It is not there in textbook. Fine. This shows that 100% starts from here, 5% is diverted, 95% delivered into collector. Now, in the collector, these electrons are repelled this way. Look. Fine. And both these electronic currents combine here to give you total electronic current to flow in this direction. Correct? I am showing you how the electronic currents are getting dissociated. I mean, how they are getting divided. Look, this way. Correct? This is the junction from which they depart, and this is the junction from which they associate. This way. Fine. So here it is 100%, here is 5%, here is 95%. Got it? Fine. Now, this part of the circuit is called input part. This part of the circuit is called output part. Input, output, input, output. In both the parts, this base is common. That's why we call this circuit as common base connection. Common base connection. Okay, fine. Now tell me, electronic currents are this way, then what about electric currents? Electric current would be just opposite. Opposite to this is this. Correct? It is IB, base current, which is flowing through base. Opposite to this is this, which is coming from emitter, so we call it emitter current, IE. And opposite to this will be this, flowing through collector, so I just show it by symbol IC, which is called collector current. Come on, IB means base current, IE means emitter current, IC means collector current. Now just apply Kirchhoff's first law at this junction. You know Kirchhoff's first law, current flowing towards the junction should be equal to current flowing away from junction. Current flowing towards the junction is right now IE, correct? And current flowing away from junction are IB and IC. IB and IC, okay, come on. This IB and IC, they flow away from junction. Current flowing towards the junction should be equal to current flowing away from junction. So IE is equal to IB plus IC. And as such also you know, this is 5%, this is 95%, so total has to be 100%. This relation holds good in any type of connection of any transistor. In any type of connection of any transistor, this relation is true. IE is always equal to IB plus IC. Got it? Fine. Now, here we define one quantity called current gain. And because we are talking about unidirectional current, that is DC, we call it DC gain. DC gain, direct current gain. Now, how is the definition? Very simple. Ratio of output current to the input current. Ratio of output current to the input current is called current gain. Here we are talking about DC gain, okay, direct current gain. In case of common base circuit, this current gain is shown by symbol alpha DC. For common base, it is shown by symbol alpha DC. And when you want to determine output and input currents, you should hide this central middle common terminal, you should hide it. This common terminal is right now base, just hide it. This is the output, this is input. In the output, what is the current? IC. In the input, what is the current? IE. Come on. Output upon input, so it is IC upon IE. IC upon IE. Because it is current upon current, it is unitless and hence dimensionless also. Correct? Fine. Now tell me, when this is 100%, this is nearly 95%. So 95 upon 100 means 0.95. 0.95 means less than 1. So I am writing here alpha DC is less than 1. Correct? Now let us go for second type of connection, which is common emitter. Not described using this figure in the textbook. just for your kind knowledge, let us see this figure also. Here you had kept this transistor horizontally. Here we are keeping this transistor vertically. Fine. Now this is the part having smallest volume, which we call base. This part having largest volume called collector. And this part having intermediate volume is called emitter. If it is NPN transistor, you should write NPN, or you may write NPN this way, no problem. Fine. What did I say just now? In any circuit, remember, emitter junction is to be given forward bias, collector junction is to be given reverse bias. If emitter is to be given forward bias, then N with negative. Look here, N with negative. So here is a battery whose negative terminal is this, and N with negative. So it is given forward bias. And what about collector? It should be given reverse bias. So N with positive, N with positive. Correct? Fine. Now this battery which is connected to base, its EMF you must show by this symbol according to textbook VBB. And EMF of this battery connected with collector, I just show it by symbol VCC. Correct? Fine. And now let us start the working of this circuit. Because of this negative terminal connected here, potential at this terminal is negative, which repels this majority charge carriers in N-type semiconductor, which are free electrons. They are repelled this way. So now electronic current starts from here this way, correct? Fine. And then out of 100% number of electrons which are entering from emitter into base, hardly maximum 5% of electrons associate with the holes. Fine. Remaining 95% is delivered into collector. And those electrons which have been associated with the holes, they will simply jump from one hole to another hole on the left side this way. They will try to come this way because potential of this terminal is positive with respect to this terminal. Correct? That is why. Then electrons will be jumping in the form of bound electrons, and they will be flowing in the outer part of the circuit this way. Fine. And then the 95% of electrons which have been delivered into collector, they will push these electrons this way. And then electronic current will flow this way. And both the electronic currents will associate, will combine here at this junction, and total electronic current will flow this way. Correct? I am showing you how the currents are getting divided. Look here this way. Correct? This way. Fine. So this is how the currents are getting divided. We have talked so far about electronic currents. What about electric current? It is just opposite to electronic current. Come on, opposite to this is this. This is the current coming from emitter, which we call emitter current, IE. Fine. Then opposite to this is this current flowing through base, which we call base current, IB. Opposite to this is this, which is the current flowing through collector. We just show it by symbol IC. Come on, emitter current, base current, collector current. Come on, apply Kirchhoff's first law here at this junction. Current flowing towards junction should be equal to current flowing away from junction. Current flowing towards junction is IE, currents flowing away from junction, there are two currents, IB and IC. Current flowing towards junction should be equal to current flowing away from junction. In short, IE should be equal to IB plus IC. Once again, we have got the same relation, IE equals to IB plus IC. Okay, fine. Then tell me here, what about current gain? For common emitter, the current gain is shown by symbol beta DC. Here for common base it was alpha, now here it is beta. The definition remains same, output current upon input current. When you want to determine output and input current, you should hide the common terminal. Common terminal is right now emitter, just hide it. Then this is output, this is input. What is the output current? IC. What is input current? IB. Output upon input, so it should be IC upon IB. IC upon IB. Again it is current upon current, so it is unitless. Correct? And tell me, when this is 5% approximately, this is 95%. So 95 upon 5, 95 upon 5, that is 19, which is much greater than 1. So beta DC value is much greater than 1. Correct? Alpha is always less than 1, beta is always greater than 1. Hai? Now, we go for studying static characteristic curves of NPN transistor connected in common base mode. What do you mean by static characteristic curves? First of all, tell me, what do you mean by characteristic curve? Characteristic curves means graphs of current versus voltage. They are called characteristic curves. But without connecting any load resistance with a transistor, if you obtain graph of current versus voltage, then those curves are called static characteristic curves. Okay? If you desire, you may connect load resistance with a transistor, and then again you can have these graphs, but then those graphs are called dynamic characteristic curves. In our syllabus, we have to study about static characteristic curves. Okay? Fine. Come on. We have to study static characteristic curves for common emitter circuit. Common emitter circuit. Not common base, but common emitter. Common emitter. And here you just show the circuit symbol for NPN transistor. Because it is NPN transistor, come on, arrow is shown on the emitter and that too outward. Fine. This middle terminal is base. Without arrow it is collector. With arrow it is emitter. This part of the circuit is input part. This part of the circuit is output part. In the input and output, emitter is common. That's why we call it common emitter. Common emitter. Okay. Now, how to prepare the whole circuit? I am showing you the importance of each component. I will explain you its function also, and gradually we will see the whole circuit. Look, first of all, tell me, with emitter, what do we require? Come on, emitter junction is to be given forward bias. So, N with negative, N with negative. Come on, for that we just take one battery whose negative terminal is connected with a emitter. Okay? And this is the battery which is connected with base. So, its EMF is shown by symbol VBB. Correct? If lower terminal is negative, naturally upper terminal will be positive. First of all, you do one thing. You connect this battery first of all with the fixed terminals of a rheostat, say RH1. These are the fixed terminals. And the variable terminal of that rheostat should be connected with a base. Now, in order to measure the voltage between base and emitter, we connect one voltmeter in parallel, which will measure potential difference between base and emitter, which we also call input voltage. Input voltage. Fine. But here the current passing through base is found to be of the order of microampere. So, to measure that current, we connect one microammeter in series, which measures base current IB, which is also called input current. Input current. Because upper terminal is positive, this also must be positive, this also must be positive. When this is positive, naturally this will be negative. When this is positive, this will be negative. Correct? Fine. What about in the output part? Come on. Collector junction is to be given reverse bias. So, N with positive, N with positive. So, just consider a battery whose upper terminal is positive, which is connected at a collector. Fine. When upper terminal is positive, lower terminal will be negative. This reverse voltage is more than this forward voltage. That's why here we show two batteries. First of all, just give the symbol to the EMF of this battery. EMF of this battery, which is connected with collector, is to be shown by this symbol as per the textbook. VCC. Fine. Now, this total terminal voltage of this battery, first of all, we deliver it to the two fixed terminals of the second rheostat RS2. So, this battery is connected across the second rheostat, and then after its variable terminal is connected with a collector. Fine. Now, to measure voltage between collector and emitter, we connect one voltmeter in parallel, which measures potential difference between collector and emitter, which we also call output voltage. Then, in order to measure current passing through collector, which is of the order of milliampere, we connect one milliammeter in series, which measures collector current IC, which we also call output current. Input voltage, input current, output voltage, output current. Once again, input voltage, input current, output voltage, output current. Okay. When upper terminal is positive, here we should show positive sign, here also positive sign, here positive, then here negative, here positive, then here negative. Got it? Fine. Now tell me, in the direction of this arrow, you should start the current, and because that current is coming from emitter, we just give it symbol IE, that is emitter current. After coming to this junction, will be divided into two parts. One part of the current flowing through base is called base current IB. Another part flowing through collector is called collector current IC. Come on, IE will be equal to IB plus IC. IE is getting divided into two parts, IB and IC. So naturally IE will become on IB plus IC. Fine. Now here, how to draw input static characteristic curves and how to draw output static characteristic curves. There are two types of static characteristic curves. One is input, another is output. Let us see these curves one by one. First of all, we go for input characteristics. Input characteristics are the graphs of input current versus input voltage. That is IB versus VBE. Come on, IB versus VBE. But such graphs are to be plotted keeping some fixed constant value of output voltage. Suppose first constant value of output voltage I want to keep say 2 volt constant. For that what you should do? You should just change the position of the variable terminal of this rheostat till this voltmeter indicates 2 volt. Once you get observation in this voltmeter say 2 volt, then after you should not disturb this position of variable terminal. Okay? Then this will be held constant equal to 2 volt. And then after you should change the position of this slider terminal from this rheostat, and then when you change the position of this variable terminal, ultimately what will happen? VBE, that is input voltage, will change, and for different values of input voltage, corresponding values of input current IB you must note down practically, and then after from the observations you can plot the graph of IB versus VBE. That graph of IB versus VBE comes out to be like this. Okay, this is the graph. But this is the graph plotted for which constant value of output voltage? Equal to 2 volt. Now suppose we want to plot the graph again, but for another constant value of output voltage, say 10 volt. Come on, what you should do now? Change the position of this variable terminal such that this voltage will change. And when this voltmeter reads 10 volt, at that time you should stop disturbing this position. Okay, then don't disturb this, and then this voltmeter will give you 10 volt. That remains fixed, 10 volt constant. Don't disturb this. Okay, and now change the position of this variable terminal. So what will happen? VBE will change, and every time you are supposed to record the value of IB, and then from the corresponding values of IB and VBE you can plot graph of IB versus VBE. That second graph of IB versus VBE, come on, for 10 volt constant value of output voltage is found to be like this. Correct? This is how this input characteristic curves are plotted. Okay, fine. Now whichever part you get, almost a straight part, linear portion, that linear portion is known as active region. What is it called? Active region. Fine. Now let us go for output characteristics. Output characteristics are nothing but graphs of current versus voltage in the output. In the output, what is the current? IC. In the output, what is the voltage? VCE. So graphs of IC versus VCE, they are called output characteristic curves. But those curves are to be plotted for some fixed constant value of input current, that is IB, base current. Base current is input current. Okay. Suppose I want to keep base current constant equal to 20 microampere. Okay. What you should do now? Change the position of this variable terminal till you get 20 microampere reading in this microammeter. Once you get that reading, then after you should not disturb the position of this variable terminal. So this value is 20 microampere constant. And now change the position of this variable terminal. When you change this position, come on, VCE will change. This output voltage will change, and depending upon that, this IC, output current, will also change. Come on, record the values of IC for corresponding values of VCE, and then after you plot a graph of IC versus VCE. This is taken in milliampere, this is taken in volt. That graph is found to be like this. Look here, this is the graph. Okay. For first constant value of base current equal to 20 microampere. Now repeat the experiment for another constant value of base current, say 40 microampere. Again repeat the same procedure. Disturb the position, just change the position of this variable terminal, then this base current will change. How long you will keep on changing? Till you get observation here 40 microampere. And then don't change the position so that this IB will remain constant equal to 40 microampere. and then after you should change the position of this variable terminal so that VCE will change, and corresponding values of IC you can record, and then after you can plot a graph of IC versus VCE, and that graph of IC versus VCE is found to be like this. Okay, fine. In both the graphs, whichever portion you get, linear, straight line, correct, is called active region. What is it called? Active region. Fine. And now, these are the input static characteristic curves. These are the output static characteristic curves. Now, let us see what are called parameters of transistor. Parameters of transistor. Before that, I just forgot one thing. Suppose in the school examination, they ask only circuit diagram, correct? See, I have explained you importance of each component. Not only that, I have explained you its job also, its function also, correct? So now do enough practice for drawing this figure only, minimum 4 to 5 times, then only you will remember. But suppose in the examination, in the school, might be in the final examination, if they ask to draw circuit diagram of common emitter connection, but using PNP transistor, suppose, using PNP transistor, then you will make 5 changes. Which 5 changes in this circuit? I am showing you. First, instead of NPN, you must write PNP. Obvious, correct? We have to write PNP. PNP. But as soon as you show PNP transistor, this arrow should be shown inward. Correct? What is the third change? Third change is the reversal of directions of all these currents. Okay? Fourth, you will revert the terminals of these two batteries. Okay? Interchange positive and negative terminals. And fifth, you will just show the opposite polarities for all these meters. These are 2 current meters, these are 2 voltage meters, correct? I repeat, which 5 changes? Instead of NPN, you will write PNP. Then you will reverse the directions of all these 3 currents. Third, you will revert the terminals of these batteries, correct, VBB and VCC. Positive and negative terminals you will interchange. Then you will just change the polarity also for all the meters. And this arrow, instead of showing outward, you will show it inward. Got it? Fine. Now let us see what are called parameters of transistor. The physical constants attached, which are defined for a given transistor, which can describe the characteristics of the transistor, are called parameters of the transistor. The constants defined for given transistor, which describe the characteristics of a given transistor, are called its parameters. Which are the parameters of a transistor? In textbook, they have talked about 3 parameters. Actually, there are 5 parameters. Let us see one by one. Look, first is input resistance. Input resistance, shown by symbol Ri. Input resistance. How is it defined? Look here. Ratio of change in input voltage to change in input current obtained at constant output voltage is called input resistance of a given transistor. I repeat, ratio of change in input voltage to the change in input current obtained at constant output voltage is called input resistance of a given transistor, shown by symbol Ri. Because it is resistance, its unit is ohm, and its value is found to be of the order of kilo ohm. Okay, fine. What about second parameter? It is output resistance, shown by symbol Ro. Ro. Come on, ratio of change in output voltage to the change in output current obtained at constant input current is called output resistance of a given transistor. I repeat, ratio of change in output voltage to the change in output current obtained at constant input current is called output resistance of a given transistor. It is also some resistance only, its unit is also ohm, and its value is found to be ranging between 50 kilo ohm to 100 kilo ohm. Fine. Third parameter is called current gain, shown by symbol beta. Ratio of change in output current to the change in input current obtained at constant output voltage is called current gain of a given transistor, shown by symbol beta. I repeat, ratio of change in output current to the change in input current obtained at constant output voltage is called current gain of a given transistor, shown by symbol beta. Because it is current upon current, it is unitless, correct? Its value is ranging between 10 to 1000, between 10 to 1000, okay? Now fourth parameter, it is called transconductance, transconductance, shown by symbol Gm. M you will write below G, okay? How is it defined? Ratio of change in output current to the change in input voltage is called transconductance of a given transistor, shown by symbol Gm. See, if it is ratio of voltage to current, you can say its unit is ohm, but this is the ratio of current to voltage, so its unit is 1 upon ohm. 1 upon ohm is nothing but mho or Siemen, mho or Siemen. So unit of transconductance is mho or Siemen. Simple, fine. And now fifth parameter is this, look, it is called voltage gain, shown by symbol AV. Come on, V you will write below A this way. Ratio of change in output voltage to the change in input voltage is called voltage gain of a given transistor. And because it is the ratio of voltage to voltage, it has to be unitless. Fine. Now, in textbook they have described how to find out values of these two parameters. I am showing you. First of all, you select 2 points on this curve, okay? Let it be these 2 points, fine. For these 2 points, come on, what is the change in base current? It is this much, which is delta IB, correct? When you have plotted these graphs, you must be knowing what is there as a value, what is there, this value on this y-axis, you must be knowing in microampere. You can convert into ampere. In short, you can just find out delta IB corresponding to these 2 points. Similarly, corresponding to same 2 points, you can find out change in input voltage, that is delta VBE. Once you know delta VBE, once you know delta IB, you can take the ratio, you can find out input resistance. And because both the points are taken on the same curve for which output voltage is constant. So this condition is satisfied, correct? Fine. Then how to find out output resistance? I am showing you. Consider 2 points on this first curve, say these 2 points, correct, in the active region. Now corresponding to these 2 points, the change in collector current is delta IC, which is this much, and change in collector voltage or change in output voltage is this much, that is delta VCE. Once you have plotted these graphs, you must be knowing these values, correct? You must be knowing these 2 values. So you can find out delta IC, you can find out delta VCE. Once you know delta VCE and delta IC, you can put their values here, correct? And then you can find out output resistance. Simple? Fine. But in textbook they have not described how to find out remaining parameters. I am showing you. Before that, I require one very small derivation. Come on, GM is how much? Tell me, GM is how much? Delta IC upon delta VB by definition, okay? You just do one thing, you divide numerator and denominator by delta IB. Come on, do it. Divide by delta IB. So it is delta IC upon delta IB, and here delta VBE upon delta IB. What is delta IC upon delta IB? Delta IC upon delta IB, it is nothing but beta. So this can be replaced by beta. What is delta VBE upon delta IB? It is nothing but RI. So replace this by RI. That's why you are getting this formula, GM equals to beta upon RI. Please remember this small formula. It will be very much useful to you in the MCQs and the numericals later on in the chapter, okay? GM equals to beta upon RI. Now I am showing you how to find out remaining 3 parameters. First of all, let us see this one, beta, that is current gain. How to find out that? Look, consider this vertical line, okay? This vertical line intersects these 2 curves at these 2 points. Corresponding to these 2 points, you can find out delta IC, correct? And this point is taken on this curve. This point is taken on this curve. So you can find out delta IB, that is 40 minus 20, that is 20 microampere, that you can find out. Once you know delta IB, you know delta IC also, then you can put their values here, delta IC upon delta IB, you can find out beta, correct? Now tell me, how to find out this voltage gain? How to find out this voltage gain? I am showing you. The way you have taken here vertical line, now you can take horizontal line here, correct? Come on, take the horizontal line. Come on, this horizontal line intersects these two curves at these 2 points, correct? Fine. Now this point is situated on this curve, this point is situated on this curve, for which change in collector voltage, change in output voltage will be this minus this. So 10 minus 2, that is 8 volts. So you can come to know about delta VCE. And corresponding to these 2 points, come on, draw these lines and you find out this much change in voltage, that is delta VBE. Once you know delta VB, you know delta VC, then you can put their values here, correct? Put their values here, you can find out voltage gain. And now tell me, you know current gain also, you know input resistance also, you know this current gain beta, you have found out this input resistance also. So once you know these 2 values, by taking the ratio this way, you can find out transconductance, okay? This is how all the 5 parameters of a transistor can be known in laboratory by plotting the static characteristic curves, okay? This is the importance of study of this static characteristic curves. Importance is that using those graphs, we can find out the parameters, okay?